Welcome to core of our journey is start, from exploding stars to invisible giants that bend time and space. The universe holds forces beyond our imagination. A speeding train. A rocket launch. A nuclear explosion. Each of these is powerful in different ways. For example, a nuclear bomb releases about 10 to the power of 14 joules of energy. That's enough to power a city for days. But compared to cosmic events, that's barely a spark. Scientific definitions of power. In physics, power is the rate at which energy is transferred or converted. It's measured in watts, where 1 watt equals 1 joule per second. So, a 100-watt light bulb uses 100 joules every second. Now scale that up. A supernova can release 10 to the power of 44 joules, in just a few seconds. That's more power than our sun will emit over its entire 10 billion-year lifespan. Other forms of cosmic power. But power in the universe isn't just about energy bursts. There are different types of cosmic strength. Gravitational power, the ability to bend space-time, like black holes do. Radiative power, how much energy something shines or emits, like a quasar. Magnetic power, extreme magnetic fields, like those from magnetars. Destructive power. The ability to tear apart stars, planets, or even atoms. Comparing events, instant versus sustained power. Here's where it gets tricky. Some cosmic forces are insanely powerful for just a moment, like a gamma-ray burst, which lasts a few seconds but releases more energy than our sun will in billions of years. Others, like quasars, stay active for millions of years, constantly pumping out energy. So do we judge power by intensity? Or by duration? Summary and transition tease. So, what does powerful mean in the universe? It's not just one thing, it's a combination of energy, time, scale, impact. In the next part of our series, we'll look at each cosmic contender, from black holes to supernovae, and we'll find out which one truly deserves the title of most powerful. Meet the cosmic giants. The universe is home to some of the most extreme, powerful, and terrifying objects ever discovered. They're not just big, they're cosmic giants that can bend time, rip stars apart, and light up entire galaxies. Black holes. These are regions of space where gravity becomes so strong, nothing, not even light, can escape. They don't just pull things in, they reshape space and time itself. Some are small, formed when massive stars collapse. Others are monsters, supermassive black holes, millions or even billions of times heavier than the sun, sitting quietly in the hearts of galaxies. Neutron stars and magnetars. Neutron stars, the crushed remains of exploded stars. Imagine squeezing a sun-sized star into a sphere just 20 kilometers wide. Now imagine spinning it hundreds of times per second. Even more extreme? A magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth's. They can release deadly bursts of radiation that could destroy electronics from thousands of light-years away. Supernovae and hypernovae. Let's talk explosions. Supernovae are the fiery deaths of massive stars. They shine brighter than entire galaxies for a few days, releasing more energy than our sun will in its entire life. Some supernovae become hypernovae, even more powerful, and they leave behind black holes or neutron stars. Star swelling and exploding, shockwave across space, energy pulse. Gamma-ray bursts, GRBs. Then there are gamma-ray bursts, or GRBs, short, violent blasts of pure energy. In just a few seconds, they can release more energy than the sun will emit in 10 billion years. They're the brightest known events in the universe, and we still don't fully understand them. Quasars. Imagine something so bright it outshines billions of stars, but it's coming from just one tiny point in a galaxy. That's a quasar. Powered by a supermassive black hole devouring matter at high speed. They're cosmic lighthouses, visible from across the universe, and they've been active since the early days of time. Black holes, gravity's monsters. They're invisible, unstoppable, and terrifyingly real. Black holes are the universe's most mysterious monsters, bending space, trapping light, and even stopping time itself. What is a black hole? So, what exactly is a black hole? In simple terms, it's a region in space where gravity has become so strong that nothing, not light, not radiation, not even time, can escape. They're formed when massive stars collapse under their own gravity, crushing all their mass into a single, infinitely dense point, called a singularity. Surrounding it is the event horizon, the point of no return. Types of black holes. There are different kinds of black holes. Stellar mass black holes are just a few times more massive than the Sun. Intermediate black holes are rare, and we're still finding proof they exist. But the true giants? Supermassive black holes, millions or even billions of times heavier than our Sun, sit at the center of galaxies, including our own Milky Way. What makes them so powerful? So, what makes black holes so powerful? It's not just their mass, it's their gravity. A black hole can warp space and time around it, a phenomenon predicted by Einstein's theory of general relativity. This creates strange effects. Time slows down near a black hole. Light bends around it. Anything that crosses the event horizon is gone, forever. Feeding and growing. And here's the scary part, black holes don't just sit there. They feed. When matter falls into them, gas, dust, even stars, it forms an accretion disk, a glowing ring of superheated material spinning at near light speeds before being swallowed. This process releases huge amounts of energy, sometimes more than entire galaxies. Can black holes destroy everything? Should we be afraid of them? Not really, most black holes are extremely far away. The one at the center of our galaxy, Sagittarius A*, is about 26,000 light-years from Earth. It's powerful, yes, but not a threat to us. Still, the idea of something that can erase everything, even information, is what makes black holes so deeply fascinating and terrifying. So that's the black hole, the cosmic monster with gravity so intense it breaks the rules of physics. But this is just the beginning. In the next episode, we'll explore gamma-ray bursts, explosions that make black holes look almost gentle. Neutron stars and magnetars, the deadliest stars in the universe. They're not as famous as black holes. But neutron stars and magnetars are some of the most extreme objects in the universe, tiny, invisible, and unbelievably powerful. They're the corpses of dead stars, and they can tear reality apart. What is a neutron star? A neutron star forms when a massive star explodes in a supernova, and its core collapses under gravity. But instead of becoming a black hole, the core compresses into a ball of neutrons. Imagine squeezing the mass of the Sun into a city-sized sphere, just 20 kilometers wide. In fact, a single teaspoon of neutron star material would weigh 1 billion tons on Earth. Spinning and pulsing. Neutron stars spin incredibly fast, up to 700 times per second. Some shoot out beams of radiation from their poles, like cosmic lighthouses. We call these pulsars. From Earth, we detect these beams as regular radio pulses. So precise, they can be used to measure time in space. Enter the magnetar. But even crazier? The magnetar, a rare type of neutron star with a magnetic field 1,000,000,000 times stronger than Earth's. That's strong enough to rip atoms apart. If a magnetar were just 1,000 kilometers from Earth, its magnetic field would wipe all credit cards and destroy every electronic device. Some magnetars release massive energy bursts, like the 2004 flare from SGR 1806-20, which briefly lit up Earth's atmosphere from 50,000 light-years away. Power comparison. So how powerful are these stellar zombies? Let's compare. A neutron star is dense enough to crush Mount Everest into a pebble. A magnetar's magnetic field is 10,000 trillion times stronger than a fridge magnet. And their energy bursts can outshine the sun, for a few seconds. Can they harm us? Luckily, neutron stars and magnetars are very far from Earth. The closest known magnetar is over 9,000 light-years away. But if one ever came close? It could destroy satellites, erase electronics, and possibly damage. Supernovae and hypernovae, cosmic explosions beyond imagination. Some stars die quietly. Others go out in a blaze that lights up the universe. Supernovae and hypernovae are the most violent explosions in space, and they don't just destroy. They create. What is a supernova? A supernova happens when a massive star, many times heavier than our Sun, runs out of fuel. With no energy left to hold it up, gravity takes over, and the star collapses. In less than a second, its core implodes, triggering an explosion so bright, it can outshine an entire galaxy for days. We've seen supernovae from millions of light-years away, and they're still visible. Types and effects. There are different types of supernovae. Some happen in binary systems, when one star steals mass from its neighbor until it explodes. Others mark the death of a single massive star. Either way, the result is cosmic fireworks, and sometimes a leftover core becomes a neutron star, or even a black hole. But these explosions do more than just destroy, they create elements like iron, gold, and oxygen. Yes, the atoms in your body were forged in ancient supernovae. What is a hypernova? Now imagine something even bigger, a hypernova. This is a special type of supernova, at least 10 times more energetic. It happens when extremely massive stars, over 30 times the Sun's mass, collapse with even more force. Some hypernovae are linked to gamma-ray bursts, focused beams of energy that shoot across space at near-light speed. If a hypernova occurred close to Earth, we might not survive it. Real supernovae in our galaxy. The last supernova seen in our galaxy was in 1604, over 400 years ago. But we know one is coming. The star Betelgeuse, in the Orion constellation, is a red supergiant nearing its end. When it goes, it will light up the night sky, visible even during the day, but don't worry, it's about 640 light-years away, so we'll be safe. Why it matters? Supernovae and hypernovae are not just explosions. Gamma-ray bursts, the brightest blasts in the universe. They last just seconds. But in that time, they release more energy than the Sun will in its entire 10 billion-year life. These are gamma-ray bursts, the most powerful explosions we've ever witnessed in the universe. What are gamma-ray bursts? Gamma-ray bursts, or GRBs, are intense, high-energy flashes of gamma radiation that come from deep space. They're so powerful, they can be seen from billions of light-years away. There are two main types. Short GRBs, which last less than 2 seconds. Long GRBs, which can last up to a few minutes. Both are incredibly energetic, and incredibly dangerous. What causes GRBs? So, what causes these cosmic flashes? Short GRBs are believed to come from the collision of two neutron stars, a cosmic crash that also creates black holes. Long GRBs are triggered by the collapse of massive stars, similar to hypernovae. When the core collapses and powerful jets of radiation are shot into space. How powerful are they? Let's talk numbers. A single GRB can release more energy in a few seconds than our Sun will emit in 10 billion years. The most powerful GRB ever detected, in 2022, nicknamed the Boat, brightest of all time, was so intense, it affected Earth's atmosphere, from 2 billion light-years away. Are GRBs dangerous to Earth? Could a GRB hit Earth? Technically, yes, but the chances are extremely low. If a nearby GRB was aimed directly at us, it could strip away our ozone layer and trigger a mass extinction. Some scientists believe a GRB may have caused one of Earth's past extinction events millions of years ago. GRBs also help scientists study extreme physics, the formation of black holes, the behavior of matter at near light speed, and even test theories about the early universe. Every time a GRB is detected, telescopes all over the world, and in orbit, swing into action to learn more. GRBs also help scientists study extreme physics, the formation of black holes, the behavior of matter at near light speed, and even test theories about the early universe. Every time a GRB is detected, telescopes all over the world, and in orbit, swing into action to learn more. Quasars and active galactic nuclei, beacons of the early universe. Imagine an object so bright, it outshines entire galaxies, yet it's smaller than our solar system. These are quasars, cosmic beacons powered by supermassive black holes, shining across billions of light-years. What is a quasar? A quasar, short for quasi-stellar radio source, is a type of active galactic nucleus, or AGN. At the heart of nearly every galaxy lies a supermassive black hole. When that black hole starts feeding, pulling in gas, dust, and stars, it releases unimaginable energy. The material forms a spinning, superheated accretion disk, and powerful jets shoot out from the poles at nearly the speed of light. Why are quasars so bright? Why are quasars so bright? Because of friction and gravity. As matter spirals into the black hole, it heats up to millions of degrees, releasing radiation across the spectrum, especially in X-rays and visible light. Even though the black hole itself emits no light, the surrounding disk glows with the energy of trillions of suns. Where do we find quasars? Quasars are ancient. Most of them existed when the universe was young, just a few billion years after the Big Bang. We detect them billions of light-years away, meaning their light has been traveling through space for over 10 billion years. They're not just bright, they're time machines, showing us what galaxies looked like in the early universe. AGNs, the broader family. Quasars are just one type of active galactic nucleus. Other AGNs include blazars, where the jet points directly at us. Seyfert galaxies, with active but less intense centers. Radio galaxies, which emit powerful radio waves. All of them are powered by the same engine, a supermassive black hole devouring matter. How powerful are they? A single quasar can be 1,000 times brighter than the Milky Way. Its jets can stretch across millions of light-years. And the black hole powering it may be billions of times more massive than the Sun. These are the brightest, longest-lasting engines in the known universe. Why it matters, understanding the most powerful things in the universe. We've explored the most powerful objects in the universe. Black holes, neutron stars, gamma-ray bursts, quasars, cosmic forces that stretch the limits of physics. But now, let's ask the real question, why does it matter? Why should we care about things that are millions of light-years away? A mirror into reality. Studying these extreme objects isn't just about curiosity, it's about understanding reality. Black holes test the limits of gravity. Neutron stars push matter to its breaking point. Gamma-ray bursts show us energy at its peak. Quasars light up the distant past. These aren't just space facts, they are clues about how the universe works. We are made of star stuff. And here's something even more personal. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of it was forged in the heart of massive stars, and scattered across space by supernovae. You, me. Everything on Earth. We are made of the same elements as the stars. To study the cosmos is to study ourselves. A laboratory we can't build. The universe is a giant natural laboratory, one we could never build on Earth. We can't create black holes in a lab. We can't replicate the magnetic field of a magnetar. But we can observe them from afar, using telescopes and satellites. Each discovery pushes the boundaries of human knowledge, from physics and chemistry to time, energy, and life itself. Could it affect us? And yes, some of these cosmic events can affect Earth. A nearby gamma-ray burst could damage our atmosphere. Solar flares from our own sun, a mini version of these events, already affect satellites and power grids. The more we know, the better we can protect ourselves. A search for meaning. But beyond science and survival, there's something deeper. Looking at these powerful forces reminds us of how small we are. Yet how intelligent, how curious, and how capable so yes, it matters. Because every black hole, every exploding star, every beam of light from billions of years ago, is a step toward truth. If this journey sparked your imagination, make sure to like the video, comment your favorite moment, and subscribe to Core of Space to join us on our next adventure.